This is Astha Pandey. I am explaining on the topic metric space, some definitions and the concept about the metric space. Definition: let X be a non-empty set of A mapping of X cross X into R. R is the set of real numbers, that is D defined as X cross X maps to the R, is said to be a metric or distance function on X if and only if it satisfies the following axioms, that are: first axiom is M1. M1 is defined as the dxy is greater than or equals to 0, x comma y belongs to X. M2 is defined as the dx comma y is equals to 0 if and only if x is equals to y. M3 is defined as dx comma y is equals to dy comma x for every x comma y belongs to X. This is the symmetry in which x comma y and y comma x both are equal. M4 is defined as dx comma y is less than or equals to dx comma z plus dz comma y for every x y z belongs to X. This is the triangle inequality. Next, if D is a metric space for X, then the ordered pair x comma d is called a metric space, and d x comma y is called the distance between X and Y. Thus, a metric space is a non-empty set X required with a metric D on X and is denoted by the pair x, d or simply by X. Different matrices can be defined defined on a single non-empty set, and this gives rise to distinct metric space. If X is not equals to Y, then M1 and M2 imply that dx comma y is greater than 0, so that the distance between the two distinct points is positive. So the distance between the two distinct points is positive. The M3 states that the distance does not depend on the order of the points x and y. The axiom M4, known as the triangle inequality as we described above. The sum of the length of the two sides of a triangle is greater than or equal to length of the third side. The sign of equality occurring when the 3 points are in a straight line. Next, we define the pseudometric. Pseudometric is a mapping of D of X cross X into R is called a pseudometric or semi-metric for X if and only if D satisfies the axioms M1, M3, M4 of the definition of a metric on X and the axiom M2 dash, that is dx comma x is equals to 0 for every x belongs to capital X. For a pseudometric we have dx comma y is equals to 0 even if x is not equals to y. Thus, for a pseudometric, x is equals to y is equal to dx comma y is equals to 0, but not necessary, because it follows that every metric is a pseudometric, but a pseudometric is not necessarily a metric. Next, we define the usual metric. Let R denote the set of real numbers. The function D, defined as R cross R, belongs to R, defined by dx comma y is equals to mod of x minus y. For every x comma y belongs to R is a metric on R. This metric on R is referred as usual metric on R. Discrete metric space. It is defined as a let X be any non-empty set. The mapping D is defined as x cross x maps to the R. R is the set of real number defined by dx comma y is equals to 0 if x is equals to y, 1 if x is not equals to y. It is a metric on X is called a discrete metric on X. Bounded and unbounded metric space. A metric space D on a non-empty set X is said to be bounded if there exists a real number which is k is greater than 0, such that dx comma y is less than or equals to k for every x comma y belongs to X, that is dx is less than or is equals to k. Also, x comma d is called the bounded metric space. If these conditions are not satisfied, then it is called the unbounded metric space.